not the same. You don't get the same answer.
It is the same. Because the idea is, okay, because I have to switch to the e to the minus tau over cosine theta. If we're changing angles, the optical depth is the same. Even though we're going through more thicker layer of the atmosphere. That's the idea. The atmospheric optical depth is one measurement, vertical. That doesn't change. As you go through longer slices, the cosine theta takes care of the idea that you're going through what we would think of as a longer optical depth.
Are we still comparing it 5 and 35? Because 35 is that atmosphere.
Here, you figured out the optical depth of those.
That's the initial.
That is the optical depth. If you just change the angle, the atmosphere doesn't change. You changed your instrument set, you did not change the atmosphere. That's why we only measure optical depth vertically, so you get one number. Yes?
35 is the initial, right?
Yeah.
Yeah. 35 is above the atmosphere. So if we draw a diagram of this, like, here's our atmosphere of the ozone thing. We have 35 watts per meter squared. We're coming down like this. Okay? That's at 20 degrees. Okay? And as we switch to a longer angle, you should still see the same amount of optical depth. Okay? Now,
They can use the formula of the inverse of the cost. The 1 over cost, the M1 of the MT.
oh yeah,
it
you
would
can
be
use,
it would be correct too.
yeah, you can do that. Just the M is 1 over cosine theta. Those little variations don't matter that much. So the optical depth is kind of like that measurement there. If I go with different angles, I still have the same vertical measurement of optical depth. Okay? Have I answered the questions? Are you okay? Do you need me to work this out, or are you like, you got this? Anybody want me to work it out? Okay. Let's work out the second one. The second one was what angle would be necessary for a fairly harmless intensity of 5 watts per meter squared to be present? What variable are we looking for? Theta. In this equation, do we have theta? Yes, we have theta. So what we do is we solve for it. So I over I0 is going to be equal to negative tau over cosine theta. The cosine theta is going to be equal to negative tau over log of I over I0. Okay? And then you plug in, then you're going to take the inverse cosine. By the way, there's a nice little trick. These minus signs get in the way sometimes. Tell me if it's okay to do this. Now watch carefully. I0 over I. Yes. Because if you flip it, this is I0 over I to the negative 1. I could write to the negative 1 over here, and then the logarithm would pull out the exponent. Okay? So sometimes you're going to see me do that. You're going to see me just reverse the I and the I0 and drop the negative sign. Just skip to this step. Okay?
How do we see the last part of yesterday?
How do you what?
The last part.
The page was being passed around.
Yesterday. From yesterday.
The page, it's being passed around. Who has that last page? I seem to see the page. No, there is the missing page is being passed around somewhere. Somebody would find it.
Here you go. Sorry. Was it doing it?
Okay, so yeah, I can take your homework now. Today we're talking about scattering. Remember, there's really only three processes. There is absorption, scattering, and emission. So today we're at the second process. Yeah. Go ahead. Yeah. And before we jump into this, I kind of noticed from your essays, it seems like most of you have had physics, and you got into this idea of, everything about optics is Snell's law. Well, it turns out this Snell's law where you have light coming in and bending and stuff is all very nicely organized. That's a subset of what normally happens to light. It's a very careful case where you don't have stuff in there that's scattering it and absorbing and stuff like that. So I would call Snell's law what you learn in physics. They only teach you useful optics, like what would be useful for making lenses and mirrors. The atmosphere is not attempting to be useful. So you are going to have light being scattered in all different directions. You're going to have absorption and stuff like that. You're kind of covering all of this stuff beyond Snell's law, where things are nicely behaved. Things aren't as well behaved in the real world. Now you can derive Snell's law from the type of stuff I'm going to be talking about today. It can get a little bit hairy and nasty, that you have to have one beam of light is canceled out by the new beams of light that you're making and stuff like that. But usually the world isn't organized enough to do that. So we are talking about interference patterns today. And that's something you probably remember from physics. We're going to go through it a little bit more. But before we get into that, I want to get an idea of different sizes and different regimes. Because it turns out, if you're looking at the scattering per unit area, when you think of light scattering off an object, you think, oh, if I double the amount of area, I'm going to double the amount of light that gets scattered off of it, right? That just seems common sense. That's not the way things work once you get the wavelengths is about the size or even small or larger than the particle size. Things become a little funkier. So we're going to be explaining this later. But what this is a graph of is if you take a ratio of like the particle radius, like they could be the molecules in the air, they could be pollutants, they could be cloud drops, but they're particles of a certain size r, and we divide it by the wavelength. And we're making a graph of the scattering per unit area here. Now, what we are used to is when the radius of things, like us, are much larger than the wavelength, we get a constant scattering per unit area. Okay? If you take a little me and a big me, if little me is 1/2 the size, and I get twice as much light reflected off of little me. That's because I'm much bigger than the wavelength. But once you begin to get smaller, we're getting things where the wavelength. Wait a second. I'm missing something. Okay. Oh, then the next one where it's marked out. Okay. Once you get to a point where the wavelength is about the same size as a particle, all hell breaks loose, because we're getting interference patterns. And once we get to a point where the particle size is much smaller than the wavelength, then we begin to find that the scattering per unit area just drops off fairly dramatically. So this first area where we have the particle size is much smaller than the wavelength is called the Rayleigh Scattering regime. And it turns out that just about all of the particle is in the same electric field. Then it takes up only a small amount of the wave in the electric field. It's not changing across the particle. If we get to where the particle is about the same size as the wavelength, you can think of waves going through, and yeah, you have a changing index of refraction, changing the wavelength, and waves going by it, they end up interfering with each other, and that's why we get all of these weird ripples and so on, as the size of the particle relative to the wavelength changes. So we're kind of going to mention this, but we're not going to go into a lot of detailing it because it's too hard to calculate. We do it in computers. You have to use, I mean, you can work out using Legendre polynomials and stuff like that. We're not going to deal with that. Once you finally have the particle much larger than the waves, then this is what we're used to. Okay? So, a lot of what we're going to talk about today depends on being able to classify which scattering regime we're in. Do we have the wavelength much larger than the particle? Then we're in Rayleigh. If they're about the same size, the wavelength of the particle, we're in B-scattering. If the particle is much larger than the wavelength, then we're in geometrical scattering. Okay? So let's build up our intuition here. And here we're going to use as the markers, you know, if you're within an order of magnitude of the same wavelength or me, either in Rayleigh or geometrical, more or less. So let's see if we can know some things about the size of molecules. What is the size of an atom or a molecule? Anybody know off the top of your head what the number?
10 to the negative 16.
And negative 16? Or
Negative 31.
oh, you're thinking nuclei now. Now I want to do the whole atom. One atom is about 1 angstrom. And you know what angstrom is? 10 to the negative 10 meters. A hydrogen atom is actually 0.5 angstrom, about 0.59, whatever. Okay, so a molecule is about 1 angstrom. There's 10 angstroms to an nanometer. So once you start sticking a bunch of atoms together, you're getting into the nanometer. So we're going from angstroms into nanometers if we're talking about atoms and molecules. Okay? Now aerosols, I could have you guess here. Maybe you remember from something I said before, but I don't expect you to know the size of an aerosol right now. Do any of you know typical aerosol particle size?
Micrometers.
Not bad. Yeah, micron size. Okay? Micron is micrometer, 10 to the minus 6 meters. Okay? So most pollution things are about a micron in size. Usually a little bit smaller and so on. Okay? Cloud drops. Another thing I don't expect you to know, but some of you might. And these aren't the raindrops. These are the little drops that are still in the cloud that aren't so big that they're falling down. That one is about 10 microns. Okay? Now this one you'll know. Raindrops and snowflakes. If you had to give a size of a raindrops or snowflakes, what would be an estimate? Millimeters. Yeah, kind of around millimeter size. Okay? Good. Now these things have to be compared to the different forms of light. So we have the solar spectrum, which is the visible and near IR and actually UV as well. And you maybe should know this from the last couple of days. What about the wavelength of visible light, solar spectrum? By the end of this week, you better know this. Microns. Now, visible light, like yellow light, is about half a micron. The visible light ranges from 0.3 to 0.7 microns, 300 to 700 nanometers, if the other thing is very far. But if you think of visible light of about half a micron, that's a pretty good size. Thermal infrared, no reason you should know this yet, but by the end of tomorrow, you should know it.
10 to the negative 5.
About 10 microns. Okay? The thermal infrared, we're getting bigger. Now, microwave. Believe it or not, the microwaves used by satellite isn't too far off from the microwaves in your microwave oven, in your kitchen.
Centimeters?
Centimeters, kind of, yeah. Have any of you tried this? take a bunch of baby marshmallows, you know, the little tiny marshmallows, scatter them all over the bottom of your microwave, turn it on. Okay? Then leave it for your roommate to clean up. But you're going to see this kind of ripple pattern of melting marshmallows in the centimeter range. So we often use microwaves that are a little smaller than that. So we're often using millimeter to centimeter size microwaves when we're doing remote sensing. Okay? And by the way, most of the microwaves that we get, they're actually the tail end of the thermal infrared. So they're normally a thermally produced microwaves. They're what we're using in passive remote sensing. Once we use radar, then that's active, but still at millimeter centimeter range. Okay? So, given these numbers, let's go ahead and classify the different scattering regimes you're in. So we have molecules, angstrom, nanometers, and we're in the solar spectrum here, in the microns. Which one of these would that be? Rayleigh, yes. We have that the wavelengths are much larger than the size of the particles. So we're in a Rayleigh scattering regime. We're going to spend a lot of time today talking about Rayleigh scattering because A, there's a nice simple formula we can work with, and B, most of the light that scatters the atmosphere is actually scattered by Rayleigh scattering. Okay? Because this is atmospheric molecules. Okay, aerosols. I think we're going this way. So we have micron versus micron. We're in the me regime. So if you're working with aerosols, you actually have some rather complicated optics to work with because they kind of scatter in all directions and it's a little unpredictable. So that's kind of symbolizing how unpredictable it can be. And very sensitive to the size of the particles. Okay? How about cloud drops with the solar? Well, almost. I mean, we have microns versus about 10 microns. We're kind of verging into geometrical here. We're going to call it geometrical. People typically assume geometric optics here. Okay.
How are you figuring that out?
Oh, we look at the, let's do this one first. We have molecules that are in like angstrom size, 10 to the minus 10th meters, and then we have light, which is in micron size, 10 to the minus 6. So the wavelength is much bigger than the size of the particles. Okay, so if the wavelength is much bigger, we're down over here. R divided by lambda becomes very small. So now we're over here.
So the wavelength versus the molecule.
Yes. Wavelength versus the size. Okay. So this is where we're dealing with kind of small versus the wavelength. This is where we're dealing with large versus wavelength. Okay. Bring that up. Okay. How about with raindrops and solar spectrum? Still geometric. We're definitely getting much larger than the wavelength now. Okay. So if we're looking at clouds and rain and visible light, the amount of scattering is going to be proportional kind of to the cross-sectional area. All of these things added together. So of course you have the, I should say the optical depth is proportional to it. The scattering goes as kind of Beer's law. Okay, now let's look at molecules in the angstroms versus thermal infrared. 10 microns versus angstroms. Very Rayleigh. In fact, it's so Rayleigh, we're so far down here, we can easily just ignore it. So if we're dealing with thermal infrared radiation, forget the atmosphere for scattering purposes. It turns out it's very important for absorption, because it will absorb and re-emit, but it's not scattering. We kind of ignore it for any scattering. Aerosols in thermal infrared. We're microns versus about 10 microns. We're kind of in the Rayleigh, getting close to the me regime. We're going to still call it Rayleigh for now. People who do aerosol work usually ignore thermal infrared. Now there might be a little bit of thermal infrared scattering going on, but it's very tiny, so they ignore it typically. They can't ignore it when it's for absorption, but they can ignore it for scattering. Okay, cloud drops, 10 microns, 10 microns. We're in the me regime. Everything's wacky there. Fortunately, with saveless for clouds, the scattering is going crazy, but there's such strong absorption of water in the infrared that normally the scattering you don't even care about because it mainly absorption is what's happening with water. Okay, raindrops and snowflakes. Now we're in millimeters versus 10 microns. We're in geometric regime. Okay. Finally, microwaves, molecules. Any scattering of microwaves in the molecule? Very small. In fact, we're going to call it basically zero. How about aerosols in microwaves? Yeah, that's going to be Rayleigh close again to zero. Cloud drops, again 10 microns versus millimeters. We're in Rayleigh, but it's actually, you can't ignore it anymore. We're going to be talking about this because you can measure, clouds in the microwave, but often you tune the microwave so that you can always ignore the clouds. Except raindrops and snowflakes, you have millimeters versus millimeters. That's going to be kind of in the me regime. So, and sometimes, it can go, depending on the wavelength, it can go between me and Rayleigh. Actually, when we do radar looking at raindrops, we use longer wavelengths, we use centimeter-long wavelengths so that we're talking about Rayleigh scattering. So, but we'll come back. Anyway, the idea here is just to get used to the idea of comparing wavelengths to particle sizes to decide what kind of mathematics you're going to be using. You don't have to learn this and memorize this right now, but you will, by the end of the course, you'll have most of this kind of under your skin here. Okay? So, where does this come from? What's going on? Well, you have an electromagnetic wave, just like I was talking about at the beginning of the class, where you have the balloon and where your heads are bobbing up and down. So that electric wave causes the charged particle to begin to bob up and down, and then it's going to send out waves itself. Okay? So, if the charge is much smaller than the wavelength, then it's like the charge is only seeing one part of the electric field at a time. So it's not like the particle is rippling like that. It's all going up and down together. And then we get this nice circular wave. Now if the wave fits, if you have several waves fitting inside the particle, then you have this kind of stuff going on inside the particle. You get really complicated stuff. That's later. Okay? So a single charge responds to a circular wave. If I have a bunch of charges here, you see how all of these different waves are adding together, and you begin to get that more complicated pattern that I'm talking about. So it's nice if you have the charge small enough that they all kind of go up and down at the same time. Then you get a nice clean pattern coming up. So that get into me or even into geometrical optics eventually. Okay? So, let's talk about ripple tanks for a bit. Talk about scattering. And I'm going to go ahead and turn off the light. And I need to get rid of that. Okay, so when I start out, I'm going to make a single point charge radiate here. And when I do that, you see the circular waves coming out. Okay, and then they're being reflected from the side, so you get some more complicated interference. If I put 2 point charges together here, look at how the thing changes a bit. We have these 2 waves coming together, and they're making, well, not quite a figure eight, almost kind of like this oval type thing. Okay? We're beginning to build a wave front. Let's pack it up with 4 oil together. You see the kind of flattened oval shapes that I'm getting there. And where is most of the wave going? It's kind of going forward out front. So you can see there's almost a little bit of flatness along the top of the wave there. You know, perpendicular to the force, you see almost a flat wave beginning to come out. We can't really, if I put tape across here, it's going to look the same. It's going to be a little bit stronger. But it turns out that a bunch of point sources added together. I can do this one. I can do that one. It's basically the same. So a bunch of point sources, a bunch of circular waves added together can begin to make almost a flat square wave going out. You do a bunch of these together, you begin to get your geometrical optics, which you're used to, where you have, you know, flat waves traveling out and then bending around things and stuff like that. Okay? So this idea that everything can be built up of circular waves is very important for understanding what's going on with the interaction between waves and particles. And you can really reduce everything and build up any type of wave that you want of circular waves. And this is important because atoms and molecules are made up of little charges, and those little charges are point sources of waves. They all have to add up to give the full wave pattern that we end up seeing. Okay? So if you take an advanced course in optics, everything is circular waves being added together. That's really what it comes down to. You can make any wave you want out of it. So let's take this idea of circular waves and look up when things might be scattering forward and scattering backwards. And so here I have a small little charge, and I'm going to send a wave past it, and it's going to produce waves going out. But the forward wave is lining up with the driving wave. But what's happening in the other direction? It has to be symmetrical, right? This wave doesn't look like that wave. The backward wave is out of phase with the driving wave, in a sense. It's going in the opposite direction. So does that little image there make sense? Yeah, same thing going off in the opposite direction, but it's a different type of symmetry. Okay, well that's very good and fine, but what if I put a bunch of these guys together? What ends up happening is in the forward direction, all the waves are being phased. You get this nice forward scattering, but what's happening in the backwards direction? They're canceling out. Okay? And you see this in real life. Light comes through windows in the forward direction. It's a forward scattering type of thing. If I take the same window and I grind it up into little pieces, so it's like table sawdust, what happens? If you shine the light and salt, what do you see? Some light is going forward, but it's also going back. It's going in all different directions, isn't it? You've got this type of situation, where if you have everything nice and organized in a smooth, large particle, you end up with this situation where light goes through.
What's the driving wave? Is that the induced wave that we're looking at? Or?
That would be like the sunlight coming through the window. And what you see coming on the other side of the window is not the same sunlight. What you see coming from the other window, it started these things vibrating up and down. It produces a wave which would be out of phase with the original wave. Because as you know, as the sunlight comes through the window, the wavelength shortens. And then when it comes out, it's not in step with what would have been the original wave. So you're actually, the window itself is producing the light that you see coming through the window. That's not the original sunlight in a way anymore. It actually scattered light. Okay, that's why you're going to ask. Yeah. So it is kind of freaky to think, no, that's not the same. If you cut a hole in the window and then you look at the light coming through the hole and the light coming through the glass, it's not the same light anymore. It's been changed by the window.
So that point right there is on the window, the scattering, right?
This would be like if you ground up the glass and you have little tiny particles of glass floating there in the window. You'd get something like this. So if you have the ground up glass, it's going to be reflecting backwards as well as forwards, I mean, actually in both directions.
So the light coming through, the first wave coming through the glass, is that one wave or is it one glass and then light is coming?
This is the glass made up of molecules. You have one wave. This is like the wave that would be driving it, and then these are the extra waves being produced by the glass.
Okay, so let's say light comes to the glass, or when
Yeah.
it's in the glass, we're looking at the reflection from the glass that way and this way?
Yeah. Yeah. So this would be like what's going backwards, and this is what's going forwards for the glass.
And then the driving force for the other ones, the particle going up and down, creating the waves, this is a particle within the wave?
This would be like sunlight coming past a small particle.
No, the one before. That one right
This
there.
one, yeah. This I've wrote. I mean, this wave really should not be going this way. It should be going. I can't drive the way it really goes.
That's a particle within the wave.
Yes, the particle. It like this is a beam of light that hits that particle. I mean, of course, the beam of light keeps going, but the particle begins to produce its own waves. Yes, it's like the corks in the pond. So again, we have the beam of sunlight, and then it causes the particle to start popping up and down. And if you have a bunch of them, then all of those secondary waves add up together in the forward direction, but they cancel out in the backwards direction. And that's why we get forward propagation of light through glass. But not if you grind up the glass, then it's scattered in one direction. Okay? Makes sense so far? Yeah.
So how do you say like wave has the same frequency both? Because like when you apply force here, it also has a there's also a constant force, right?
Yeah. It turned out when the wave causes these things to bob up and down, the wave will lose some of its own energy and transfer some of the energy to the particles that makes it bob up and down. Just like, ocean waves will lose energy as it makes ships bob up and down and stuff like that. So you can think about it as force, you can think about it as energy. Okay, so yes, the electric field of this driving wave will be decreasing as it goes through because it's giving up. It's applying force to these things and using energy in the process. Okay. And that's actually a good point because that's why I'm saying you don't see the original sunlight anymore. It's all been taken up by the window, and the window is reproducing the wave. Okay. So the introduction of the kinds of things that are going on. Let's talk about Rayleigh scattering. So this is when the particle is much smaller than the wavelength. So here I have two different particle sizes. And I'm going to keep doing the same mixed metaphor where I show a driving wave coming in one direction and the radiated wave may be at 90 degrees, but I think you'll get the idea here. So if I have a driving wave coming that way, it's going to make those particles oscillate. And they're going to go bobbing up and down and they send out their own circular waves.
Does the pattern of this particle depend on this form of the particle, the shape of the particle?
Good question. If the particles are very small compared to the wavelength, it kind of doesn't matter because they're all bobbing up and down. And yeah, close to it, you're going to see something that looks like the outline of the particle. But as you get further away, it kind of merges more into a circle. So those fine little details of the particle shape are only noticeable if you're very close. And it kind of begins to flatten and become more circular as you get further away.
So it doesn't depend on this shape of the particle, but it's just when it's very small, if you break,
Yeah.
kind of vibrates.
And if the particle is very small compared to the wave, you don't need to worry about the shape of the particle. Once it becomes bigger compared to the wave, then yes, you need to worry about the shape. But they're very small, it's just a collection of charges.
So that's the like normal path, like a particle with uncurrent when it's
Yeah.
hit by a wave. You take the energy of that wave and it's
Yes. Yeah. If these were squared, they kind of look like rounded squares, and as you get further and further out, the rounded part would take over, and once you're far enough away, they take a circular wave. Okay. So we have two sides. Note that the larger particle with more charges in it produces the bigger wave because you have more charges going up and down. So that just makes sense, right? Okay. So the number of charges is going to go as the volume of the particle. It's going to go as the cube of the radius of the particle. So we can already see that the amount of wave produced is going to go at least as r cubed. So it's going to increase faster. We were talking about energy per area or light reflected per area. Which increases faster with radius? Volume per area. Volume increases faster with radius. So we can already see that the amount of light scattering is going to increase faster than the area. But a little bit more than that is going on. Because the number of charges per volume is going to go as r cubed. That's going to give you that electric field. Okay, so the electric field amplitude will go as r cubed. However, if you remember your physics, what we're talking about here is the energy, not the electric field force. The energy of an electric field, does anybody remember how energy goes with the electric field wave? They may not, because it's a square, an amplitude squared. So the E wave intensity, which is the energy, goes as r to the 6th power. Okay? So that means that the intensity, energy per scattering area, is going to end up going as radius to the 4th power. So that was that curve you were seeing at the front in the Rayleigh scattering. However, it's also going to change depending on the wave itself. So here we have an electric wave, the same thing we drew about. You have your typical dipole pattern there. So the electric field amplitude, again, if we're going back to your physics, it's going to be proportional to the acceleration of a particle. Okay? It's force, acceleration, it always goes together. So it's going to go as the acceleration. Now, the acceleration is the second derivative in time. So it means it's going to go as frequency squared, which means it's going to go as 1 over wavelength squared. Okay? And then we have to do the same thing again. E field intensity goes as square of the amplitude, 1 over wavelength to the 4th. So we put it all together. The scattered intensity per area is going to go as r over wavelength to the 4th power. And that's our Rayleigh formula. Okay? No, you don't have to remember all of this. However, if you're like me, you feel more comfortable if you don't have if I'm not just pulling a formula out of my back pocket there. I'm at least telling you, it does come out of known physics. But r over lambda to the 4th power is the amount of scattering per area if we're in the Rayleigh regime. So this is what we're going to be playing with for most of today. Okay? So, we're getting more of that stuff. So, what we're saying here is that we have scattering coefficients at 2 different wavelengths. And the ratio of these scattering coefficients, if we have one particle, r over wavelength 1, r over wavelength 2. And then the r's would cancel out. The ratio of the scattering with wavelengths would go as the wavelength, ratio of the wavelengths to the 4th power. So, notice how there's this reverse here.
So it's the same particle, but,
The same particle looked at with different wavelengths. So this is how the scattering will change. So, as we're going from one scatter, so let's say we go lambda 1 is a short wavelength, lambda 2 is a long wavelength. Where am I going to have more scattering? In the long wavelength or in the short wavelength? Actually, it reversed. These flipped over. The short wavelengths will have more scattering. And this should make sense because short wavelengths have the higher frequency, right? Higher frequency will make things bounce up and down, but have more scattering. So short wavelengths scatter more than long wavelengths if we're in the radius. And it scatters more going up to the 4th power. So these are the scattering coefficients. If we're only talking about scattering and not absorption, the optical depth just goes as the scattering. Everything else is going to cancel out. The optical depth will also go as the ratio of the wavelengths to the 4th power. So, we're talking about visible lights. We have blue and we have red. If we're talking about scattering, and in the atmosphere, which should have more scattering, the blue or the red? Okay, if we're talking about scattering the atmosphere of visible light, this is going to be the Rayleigh scattering because the molecules are smaller than the wavelengths. Which will scatter more, blue light or red light? Which has a shorter wavelength? Blue light will scatter more. And scattering means it's going in all different directions. What's the color of the sky? Blue. Rayleigh scattering. The sunlight is hitting on different parts of the atmosphere, but some of it is being scattered back towards us. That's why we see blue. Okay? Because of Rayleigh scattering. Okay? And in fact, we can see that here. This is the scattering. This is the transmittance. If more light is being scattered, less light is being transmitted. We have lower transmittance in the blue, and then it picks up as we go towards the red to longer wavelengths. So this background of scattering is stronger in the blue, weaker as you go towards the red and near infrared and stuff like that. Okay? That's where that comes from. So, we're going to do a little practice problem here. 96% of red light at 700 nanometers is transmitted through the atmosphere of solar zenith. That actually came from 700 nanometers. We're up there about 96%. Okay? How much blue light would be transmitted at 400 nanometers? So, I could just leave you here to stew over it a little bit, but let me at least get you started.
70%?
Not that easy.
54.
But if we're talking about transmission, what other variable do we need to think about? Optical depth. So what should be the first thing that you do? Figure out your optical depth. Okay? Start there and then see how the optical depth in red light should be related to optical depth in blue light. And again, I should be careful. We're talking about the direct beam here, not the secondary scattering. So we can use here as well. Yes, do have what you're aiming for. First we have to figure out one optical depth. Figure out one optical depth. Then you know the ratio of one optical depth to the other. That's what I want to do. Yeah, first get the optical depth. Yeah, if you're not giving an angle, just assume it's vertical. Wait a little longer, we're going to ask how many of you are stuck right now? How many of you are stuck? Okay, let's start working this through. We have two wavelengths and we have a percentage, so you look at it and say, what am I supposed to do with this? Well, we have a percentage transmission. Do ray begins to popping, think transmission, we thought optical depth. When we think optical depth, what's the one formula?
Beer's law.
Beer's law. Okay? So we know Beer's law goes something like this. I over I0 is equal to e to the minus tau. Do we have an angle to worry about? We're just going to set cosine theta equal to 1. Okay, so we have this nice. Where does 96% come in? There you go. Okay, so we just change it to a 0.96. And you can figure out the optical depth, right? But that is the optical depth in the red light. How do we figure out what's going on in the blue light?
Compare the two wavelengths.
Yeah, the ratio of the wave. Okay, so let's first figure out. So in the red, you guys should have gotten about 0.04. Okay. Which, by the way, you could have guessed. 0.08?
No, it's 0.04.
Okay.
Yes. Yeah, it's 0.04.
Yeah, about that, if you round it off, okay? Point like 0.38 or something like
I have a
that.
question.
Yes.
Can we just determine that by the transmittance?
Yes, because in this case, it's pretty clear the optical depth is very small. So you can do the transmittance is equal to 1 minus optical depth if you have high transmittance between low optical depth. But you only get away with that because it's going to be very small. Once it becomes bigger, you have to use the exponent. Okay? When we go into the blue, you have to use the exponent. This doesn't work anymore. Okay? So anyway, so we have our optical depth in the red. If we want to figure out transmittance in the blue, we need optical depth in the blue. How are we going to get that?
Take the optical depth of the red and divide it by the ratio of the wavelengths to the fourth power.
Now we have to be careful here. I'm going to write wavelength in the blue over wavelength in the red. Remember, it reverses. Okay? Do we have optical depth in the blue? No, that's what we're looking for. In fact, how about if I reverse this here right now? Let's do blue over red. Blue over red, and then I'm going to do red over blue. Okay? What do we have? Do we have optical depth in the reds?
Yes.
Yes. Do we have wavelength in the red? Yes. Wavelength in the blue? Yes. We only have to figure out the optical depth in the blue now. So yeah, optical depth in the blue is going to be optical depth in the red times wavelength red over wavelength blue to the fourth power. Plug everything in. 0.04 times like 7 over 4. Everything's going to cancel out in the fourth power. And what do we end up with?
0.12. 25.
25.
0.1225.
Is that right? That seems a little low to me.
0.375.
Yeah, that sounds right.
0.375.
Yeah, 375. Did you forget the fourth power over there? Okay, the 0.375. Now that we have the optical depth in the blue, how do we get the transmitted light in the blue? Same thing we had before. Good. Transmittance equal to I over I0 e to the minus tau, but this time we're going to put it in the blue. If you do that, you're going to get 0.68. Okay? Which is 68%.
The online student, they cannot see the board. So
Oh, okay.
by the the I is 7, the I is 4.
Well, we don't know what either of those are, actually. But we're looking for the ratio, which is the transmittance. Now, that's something important to remember. In this formula, because we have I over I0, if we're talking about transmittance, that is I over I0. You don't have to know I or I0, you just need to know you're looking for the ratio. Oh, yes, yeah, thank you.
Yeah, that's the
Very important.
What is important?
It's not I over I0 times this, I over I0 equals this. Okay? Yes?
Yeah, just what we did with the negative sign.
What
in the
did-
beginning?
Yes. You just, is, when you take the logarithm of something less than 1, it's negative, so we're going to have a negative times a negative, it becomes positive. Yeah, negative would take care of itself.
68%.
Okay, so what are the range of optical depths in the atmosphere across the visible spectrum? We've already done that, haven't we? From 0.04 to 0.375. That's the range of optical depth of the atmosphere.
So we could still have used like, because before solving the problem, I used the graph to like guess.
Oh, yeah.
The percentage of the blue wavelength.
Yeah. Now, I don't know the full origins of that graph, and I don't know if they have aerosol in there and stuff like that. So, I'm not sure I'd put complete faith in that graph. And of course, that also, continue in a second. The other thing about the graph is, I think it may include multiple scattering, which we're not doing here. So once you get to larger optical depths of scattering, it turns out you have to add in the multiple scattering. So I'm not sure exactly what the graph does. I think it does include the multiple scattering.
I'm just curious as to where 4 came from again. 4 and X1. T red.
That's what we had.
Oh,
Yeah. What is this? Towards tower. Yeah. And then of course you have to relate it to optical depth.
okay.
Okay. So far so good. So one of the primary ways you can convince somebody that you do know about remote sensing and radiation transfer is that you do know the phrase Rayleigh scattering when you go to the fourth tower. It's very important terminology when you're in your job interview. Yes.
So the second part of that question where it was asking for the range of optical depth,
Yeah.
would we just compare the two? Or are we looking at...
Because we have the red, which is one end of the spectrum. We have the blue, which is the other end of the spectrum. The spectrum goes from red to blue. So 0.04 to 1.4. It changes pretty much by a factor of 10 across the visible spectrum, the optical depth of the atmosphere. So it's pretty large change due to Rayleigh scattering.
The optical depth for blue light and the optical depth for red light is
Very different. Very different. Okay? Now, the other thing we want to worry about, so far we've been drawing circular waves for Rayleigh scattering, but remember, it's a dipole pattern. It may go circular out there, but as you move away from the axis, it's going to look different. So, here's the idea. I have a driving wave, going to get hit a charge, going up and down, and notice how the amplitude changes as you go out of perpendicular with the axis of vibration there. So the circular wave is this if I'm doing like around this axis, but if I'm going out of that axis, I have to look at how the amplitude will change. So what we're getting here is we get an amplitude pattern kind of like a figure eight. As here's the maximum amplitude, the amplitude decreases down to 0, and then the amplitude picks up again, and stuff like that. That's if you're looking off axis. That's the type of pattern we get. So this would be, we may call it the Y polarization. The intensity is going as cosine squared. Why is it squared? This pattern is that the amplitude goes as cosine. Intensity is amplitude squared. So it's cosine squared. You may be wondering why is he talking about intensity? Intensity refers to the energy of the wave. So we're always worried about the energy of the wave is going to be amplitude of the electric field squared. So we're going to get one polarization. We're going as cosine squared of the angle as you go off the axis. If we have a driving wave like that, and this thing is being driven up and down, then we're going to get the same intensity in all directions. So it's kind of like if I have this electron bobbing up and down like this, all of you are going to see the same intensity. It doesn't matter which direction you're looking at, right? But if I go like that, how much of the pen do you see? Is it pointing right at you? Almost nothing, right? How much do you see? You see almost the full length. So it depends on what direction you're looking at. So we have these two polarizations. We have one polarization, we have another polarization. We assume that light is made up of all of these random things, so we're going to get this pattern, which is a figure 8, added to this pattern, which is a circle. And that's what we're going to call the Rayleigh phase function. It's a combination of the circular, because some waves are going like this, and that pattern, because some waves are going like this. Okay? Or combinations of the two in between.
So what does the polarization represent again?
If you have like a wave in a pond going up and down like this, okay? So its axis of polarization is the direction of the vibration. If you look at it sideways, you're going to see kind of getting a different view of what the wave is doing. So again, if the electron is bobbing up and down like that, all of you are going to see the same thing, but if it's bobbing up and down like this, depending on the angle, you're going to see something different. So these are two polarizations of light that we're talking about. Okay, so we add those two together. It turns out if you integrate it, you want to integrate it to one. This phase function is the term for it, is what fraction of the scattered energy do you see as you look at different angles? So this is the angle from the direction of propagation of light. Okay? So we're going to come back to that in a little while, but this is telling you how much energy is coming towards you if you're looking at different view angles.
What dictates the 3/4?
And that's because what we want to do is we're looking at the fraction of total energy. So if we're looking at all directions and add it up, we want that fraction to come out to 1. So if we integrate this over all angles, you're going to need 3/4 to make it come out to 1. We could go through that whole integration process, but it's not worth it. It's a normalization factor. So, having been introduced to that idea, we got another little demonstration here. Probably should have done this one earlier. We're going to give you a 5-minute break to contemplate the Zen pattern there at your lectures. And I have been just leave it out there for a couple of days and come back and use it again. But milk can't be left out. It coagulates, it rots. It ruins the demonstration because it's no longer the same properties of milk that you had before. I think it smells a little bad too when you open it. So it has to be kept in the refrigerator. So, again, milk looks white because it has droplets which are fairly small, a little bit smaller than visible light. So that means it's going to scatter in a bunch of directions. However, it's not that small compared to light. It's a little bit smaller than visible light. So here I have white light. What is white light composed of? All the wavelengths, okay? I'm going to put in a little bit of milk here. And I don't want to put in too much. That's not enough, though. as I mix it in, do you notice a tint beginning to occur here? Yeah, what color? Orangish, reddish, I'm going a little bit more. Okay, can you see the kind of orangish, reddish tint to it there? I may be using the power of suggesting a little bit, but
That's what's supposed to be.
there it is. You are seeing a little bit of a reddish orangish tint, and a little bit more.
Oh, okay.
Especially if you come off the lines in front of the glass.
Oh, yeah, it was looking bright. I forgot about that. Now you can see. Kind of an orangish reddish tint. Okay? So what is the red light doing?
Scatters.
Wait a minute. Where is the light coming from? Through there and ending up there. So was the red light scattered? Or was it transmitted? It was transmitted. The red light is being transmitted. What do you think is happening to the blue light? Scattered, because which wavelength scatters more? The smaller one, okay? If you look at the side of the star, let me rotate it here. What kind of color do you see there on the side of the star? It's kind of bluish. Okay, so you're seeing the blue light being scattered, the red light being transmitted. Because the metal drops are a little bit smaller than visible light. We're actually probably more in the me regime than what we call Rayleigh, but the same effect is still happening. Okay? So you're kind of seeing why the sky is blue right here. Blue is being scattered. You can look in more directions, you can see blue being scattered. Okay? Where did the lid from the middle? I put the lid on, I forgot. We're good. We're fine. So, for your benefit, I put some milk in here. Everybody's telling what is happening. What color do you see up there, more or less? Red. Okay, so what is happening to the red light? It's being transmitted. Therefore, what do you think is happening to the blue light? It's being scattered. You can see a bluish tinge here. Okay. So it's semi-Rayleigh. Like I said, I think it's more me than Rayleigh here, but it still has some of the properties of the Rayleigh scatter. Now, put this out, put it away. This begins to relate to weather radar. Do any of you know if you're going to be working with radar data? Possibly. Okay. I do have like a 6-page handout going deeper into the theory than I'm here. If any of you want that at the end, let me know. I can make copies of that. But weather radar, we have centimeter waves with millimeter raindrops. So we're talking about Rayleigh scattering. Now it turns out the cloud drops are going to be so much smaller than the raindrops, it's kind of like the Rayleigh going on towards the zero end of things. So radar, they can tune it so they can pick up clouds, but they kind of tune it so that the clouds are being filtered out. And all that you're seeing are the raindrops. Which is only possible if large things scatter much more strongly than small things, compared to the wavelength. So the basics of weather radar is you send out these microwave signals here, millimeters, centimeters, and you're going to get stuff reflecting. And notice I have the reflection from the raindrops, because those would be up in the cloud. In fact, most of the reflection you see is still up in the cloud. But the clouds are not reflecting, or at least they're reflecting much smaller, because it's already the fourth type of thing, and the drops are much smaller. So the time it takes for the signal to come back tells you the distance. as we know about the speed of light. The intensity of a return signal is used to calculate the amount of rainfall. This is easy. That's a bit more complicated. I'm going to take you about halfway through this calculation just so you can see the types of assumptions that are being made. And about halfway through, your eyes are going to begin to glaze over, and I'm going to say, okay, then we do this, and we're going to move on. But if you want the whole thing, I can give you the handout for the whole thing. So, return intensity. First thing that's happening is this light is spreading out, which means energy is dropping with distance, right? So that's going to be called distance attenuation. Then we're going to have backscatter per unit area. How do you think we're going to calculate scattering per unit area? Might we have a formula for that? Yes, it's got a Rayleigh scattering formula. Because these raindrops are going to change in size. So we have to figure out the amount of scattering for each size of raindrops, but we have a formula to do that. And then, of course, you have to get the total area, because this is backscatter per unit area. You have to figure out the area.
So the area of
the drops.
of the drops.
So this is the area of the scattering targets.
And you said distance attenuation is like the drop of energy.
Inverse square law.
Okay, so as it like
Yeah, and as some of you had pointed out, intensity drops off as the area of the sphere. It's the same energy being spread out over a larger area. It's going to go as 1 over radius squared, because the area goes as radius squared. Okay? So we have to look at every little drop area, cross-sectional area, and be adding one of those together. Now it turns out we don't do this separately from that. These two things are going to be done together. Okay? So, there's a formula. Now, I have distance attenuation. I have 1 over distance squared, but then I squared that. Yes?
is that because of the cosine law that you told us of the circle?
No, actually not because of that. It's actually simpler than that, but unless you're told about it, you may not catch it. This light goes out, the circular wave going out, it hits a particle, what do we get coming back? A circular wave again. So we have to do this 1 over d squared twice. Going out and then being reflected. There are 2 circular waves, one after another. Of course, we have the original intensity of the ray. Okay? Now we're going to sum over all of the different radii of the reflectors. Now this first one we have our sigma, that's our backscatter cross-section there. Radius to the 4th over wavelength to the 4th. That should look familiar now, right? That's our Rayleigh scattering. Now we have to get the area. How many particles are there of a given radius? And then we do pi r squared to do the cross-sectional area of that radius. Okay? So every one of these things should be, oh yeah, that makes sense. Shouldn't be that scary. Inverse squared applied twice, Rayleigh scattering, area of the particles. Main thing that's important here is this is the size distribution, how many particles you have of any given size. Okay? So, got all of that. We do some algebra. Just kind of gather up terms and stuff. So I've gathered all of the R terms together. I've gathered all of the constant terms and the distance terms together. So all of these constants, because we know the intensity of radar is going to be constant. We know the backscatter coefficient of water is going to be constant. All of that stuff, or the scattering coefficient. We know the wavelength is going to be constant. So we can gather all the constant terms into something called K. We're e to the 4th times this guy there. Okay. So notice that now we are going as a radius to the 6th power. So which is going to scatter more? Big raindrops or small raindrops? Did you guys see that R to the 6th power there?
Very fast.
I think you're seeing the same R6 power you're seeing, right? The big drops are going to scatter bigger per drop. There are actually a lot more small drops than there are big drops. But because of this 2 to 6 power, most of it ends up coming from the bigger drops. Okay. We can keep simplifying. This is kind of an interesting thing. This is size to the 6th, radius to the 6th. So we're going to redefine that as Z. And now we can write our radar equation as this. So this is the outgoing intensity and distance. Z has to do with the size of the drops and nothing else. Okay? Now this is our radar equation. Now we have to see what we can figure out from this. Yeah. K is all of the constant terms added together, combined together. So that's all of the pi and the backscatter, even the wavelength. Okay? So, this is all very nice, but we can't do anything until we have the size distribution. And this is where we might get into trouble. Because, what are you going to use for that? Well, it turns out, I think it was late 1930s or so, 40s, two guys got Marshall and Parma, did a bunch of experiments. They were measuring a bunch of storms, and they came up with the size distribution is exponential. So this is the radius. You have more of the smaller radii and less of the bigger radius dropping off exponentially. But they went even further than that. They said, say, if this is the rain rate, the coefficient is going to change with the rain rate. The way it changes is if you have heavy rain, it's actually a smaller coefficient, so it doesn't drop off as fast. So you see we have kind of more of these larger drops. And with the light rain, you're going to have more of these smaller drops compared to the larger drops. Okay?
What is C?
C is just an experimental constant. C and lab, C and H, they're all experimental constants. Okay? So they did this, just make a little bit of work kind of confirming that this sort of works. And for the decades ever since, this is what we've been using. So we just assume that those experiments are good and they're going to apply to any other storms that we see.
What do you call that constant? The rain rate constant?
There's like two constants and then that one. I don't know that there's a name for it. There might be a name for it. I don't know. But, so, we have this. So reflected intensity is going to give us Z. We have that. This is a big assumption. That's why we call it a retrieval, not a measurement. Because a lot of this may change depending on, layers of atmosphere, how dry it is, humidity, stuff like that, how mixed things are. But if we can't make an assumption, we're stuck. So we have to make an assumption and go on. Okay? So we can sub into Z with this thing, so. Now, if I take this and stick it into there, we're going to get, integral over R squared. And then you have to make assumptions about rain, how fast the raindrops fall. You can work out the terminal velocity of a sphere. But it turns out raindrops aren't spherical because they're kind of hamburger bun shaped. So you have to, there's a bunch of assumptions you have to make. I could go through a couple more pages of doing the math. But that's what's going into it. And you can figure out the rain rate from it. And in fact, you get something. What you get is that rain rate goes as some constant times Z to some power is what you end up getting. Usually you put the power in the rain rate. I don't know why they do that. That's the type of equation that you get. And that's how we do radar. But it all comes down to a bunch of assumptions that you're making. You just have to remember, okay, maybe the distributions aren't quite right. So rain rate comes from reflectivity with assumptions about drop size, diameter, and drop shape. So, the thing that you should remember about radar is A, it's based on Rayleigh scattering. B, it's based on assumptions about the drop size distribution. They're experimentally based assumptions, but they're still assumptions. And C, they're based on assumptions about the shape of the drops and the way that they're going to fall in order to get the radar. But still, it's the best we can do. It's one of the major retrievers that we have. Okay? Any questions about this before we go on? Now we're going to get into me scattering. Me scattering is where things get so complicated that actually to your benefit, because I'm not going to try to explain it. We're not going to try to do it with the math. Okay? We're just going to talk about it so you get some idea of what's going on here. So, the idea is we have waves going through a sphere and maybe around the sphere. So there's kind of like the driving wave, and there's a wave going through it. And as this is electric field going up and down, it's going to cause a dipole effect in the particle. So in this case, I happen to have two waves that would constructively interfere, but you can see they don't have to be in phase. So what we get here is this wave goes through, we have positives and negatives. It's polarizing the sphere, but different parts of the sphere are being polarized in different ways because they're in different parts of the wave. So that's a little bit complicated. And this sucker is producing more waves to go up. Remember, with the Rayleigh scattering, everything was all either bobbing up and down, was all together. Now we have things that are not all doing the same thing. I have to put one of those waves together. So maybe we're going to have waves going up like here, and these waves happen to be destructively interfering. In another direction, to be constructively interfering. They have large amplitude and small amplitudes. It's all very complicated. Okay? That's why I'm not going to make you do any math with these things. However, somebody did, Gustav Mead did it like in the 20s. He was actually trying to figure out how to fix the color of paint depending on the drop sizes of the paint particles in the, I guess, what is it, turpentine, whatever it is, to put the paint in. So yeah, this was a guy trying to work out colors of paint. And he can write a whole book about what he did. There's a few books written about me scattering. So when are we using me scattering? Well, it turns out if we're talking about visible light, what's the wavelength of visible light? Guys, look up. Micron. Micron is half a micron. And what are the size of typical aerosols in the atmosphere? Micron. We're in me scattering. Oh joy, we have to deal with me scattering. Okay? And what we're doing with LiDAR is we're sending out a signal. It's going to hit these guys, and you're only looking at the backscatter, of course. So at least, thank God, you only have to worry about scattering in one direction. Okay? But it's just like radar, you send out your positives, from time of return you get the distance, and from intensity you figure out how much material is present. Except you can't do it as easily as you can for rainfall, because rainfall has a nice, slick, little, easy formula called Rayleigh scattering. Me scattering, you're dealing with Legendre polynomials, saying like infinite series of Legendre polynomials, and it's just nasty. So you think, okay, this is hopeless, why do we even try? Well, for one thing, you do know if all of the particles are about the same size, or the same size distribution in different levels of the atmosphere, then at least you know if you get more return, you have more particles, right? So that's easy. Assuming the same size distribution, at least you can say, oh, twice as much density, twice as much return. That makes sense, okay? But let's just remind ourselves, you know, we have a driving wave here, a small Rayleigh scattering particle, a pretty simple pattern. We have a bunch of things. The backscattering is where you get all this weird interference going on. So it's going to depend very sensitively on the ratio of the size of the particle to the wavelength.
So the behavior is still the same.
What?
The behavior of the scatter
Yes.
as the
But if you can assume, you may be able to assume that, okay, at this level and that level I have the same size distribution, so if I have twice as much scatter, I have twice as much stuff. But then the next question might be is, how much stuff is it exactly? Not how much is it one layer relative to another one, but how much actual stuff do I have? Then it becomes complicated. I don't know if that made sense.
no.
Okay, you can say twice as much scattering, twice as much stuff, but how much stuff? That's a whole different question. Okay? So, to give you an idea of what's going on with me scattering here. This is Rayleigh scattering. There's our 1 plus cosine theta type thing in the red. So those are the two polarizations shown in the blue and in the black. This is if I have that the wavelength is about 1/20th, is 20 times the particle size. Okay? Now I'm going to go to the wavelength is 4 times the particle size. We begin to see mainly forward scattering already. We've got logarithmic here, so you can see mainly forward scattering, a little bit of back scattering here. Logarithmic scale. Now we go to the wavelength is twice the particle size. Here, in a linear scale, almost all forward scattering, we have to go logarithmic and we begin to see the back scattering. Ooh, look at these patterns. We're beginning to see that interference patterns, the ripple patterns coming out. If we're at the same wave, if the wavelength and the particle size are the same, I mean, look at what we can't even look at the linear one. Look at all these crazy patterns, and look at how crazy the backscattering is, stuff like that. So it's complicated to figure out what's going on. And eventually, as we get much bigger, we're getting even tighter interference fringes. It's all complicated stuff. Okay? You might think, oh, there's no hope. Well, there is hope. And the hope comes from the fact that not all the particles are the same size. If they were all the same size, you'd have to calculate stuff exactly. And you'd probably be wrong. But they have a distribution of sizes. This green is the backscatter pattern from one side, blue is the backscatter pattern from another side. And you can see there's some changes, and it's too complicated to get. But as we add a bunch of sizes together, this black line is everything added together. And you can see it's still kind of complicated. As I keep adding terms, I'm going to end up getting a nice smooth curve here. And a nice smooth curve you can work with. So what saves the LiDAR people is the fact that they don't have just one size of particle. They have a whole distribution of sizes. They add together to smooth everything out. And when they get their retrieval, they're not getting the particle size, they're getting an average particle size. And that's what they can report, an average particle size. And they know there's bigger ones and there's smaller ones, but everything averages out and you get an average particle size, which you can calculate. Okay. Are any of you doing LiDAR? I think some of you might. Yeah. So you'll find out we're going to be talking about effective radii and stuff like that. It's an average radius. They don't get a single radius.
Actually, I have a question.
Yeah.
So, how low is the forward scattering? So, you get the laser and some layer part of aerosol. You get some forward scattering from those. So, how relevant are those forward scatterings?
We don't detect it. The detector only detects what comes back down after.
No, what I mean is, so you have the forward scattering of, let's say, the first layer of particles, and then you have your laser.
Okay, you're talking about multiple scattering.
Yeah.
It's important, but I think typically with aerosols, you're talking about optical depths in the range of like 0.1 to 0.2. So if you're doing the second scattering, it's like you're only getting 20%. So it will be a term in there, but not the most important term from the first scattering and then the second scattering. So 0.2 squared is 0.04, it becomes less and less. So mainly the direct beam with a small correction from secondary scattering. Because yeah, you get the backscattering, it has to be scatter and then scatter back to you. Okay? We're almost through. Okay? So, backscatter efficiency, peaks and particle diameter is roughly equal to the wavelength. But you get all these strong oscillations. However, you can get average particle size. In fact, you want a whole distribution of particle sizes, otherwise you wouldn't be able to figure out anything. It would be too complicated. So you need all of these ripples to average out different particle sizes. Okay, so here's a little question for you. This is actually from my PhD thesis I did here. We have smoke. We have a bunch of forest fires up in Canada, and we have a smoke plume here. And then we have clouds. Now, the optical depth of the smoke plume, this is actually pretty thick, is maybe about 0.5 or 1 or something like that. Optical depth of the clouds are like 5 to 10 or so. So the clouds have a much higher optical depth, maybe 10 times as much optical depth, or we're getting about half the light from the clouds. Why are we seeing more light from the clouds than you would predict just from optical depth?
Because try and have a very small particles,
Yeah.
and it's the really pressure that's taking place.
Okay. Well, and you said the clouds or the smoke?
The smoke is
The smoke. See, nailed it. The smoke, it turns out, does have it's like half a micron or so. They're going to be scattering in more directions than the cloud particles, which are scattering more forward. Now, which way is forward here? We're up here, the sunlight is coming here. Which direction is forward? Down, away from the satellite. The smoke is scattering in more directions. You're more likely to get that light coming back up towards the satellite, because the smaller it has more of the symmetrical scatter. Okay? So when you're looking at images, it's not just optical depth, it's optical depth and the scattering phase functions are up top, the scattering pattern. You have to look at both of them. Okay? So, pretty geometrical scattering. Finally, we're getting to what we're used to. This is what we grew up with. That you have twice the area, you get twice as much light being intercepted and reflected and stuff like that. Okay? So, unfortunately, it's not as easy as, it's not as simple as you think. This is what our typical image is. You think of light waves going like that. You're blocked by an object. If you're thinking of little bullets, photons, you would go like that. Okay? That's what we're used to, right? However, in reality, light is going to be bent around the edges, which means that it's not just the direct geometrical cross-section that's affecting light. More light is being affected than just in the geometrical cross-section. And by the way, these two beams of light can interfere with each other and produce an interference pattern. And just to prove to you that this is happening, you can take your fingers, put them close together, and then look at the lights through it. And you're going to see go ahead and do it. You're going to see a bunch of little parallel lines. You have to squeeze the finger until the light won't go away. You have to look at the lights. Look at a bright light that's up above you. So squeeze them together, and if the light, if you get very close together, you're going to see a bunch of parallel lines there. Are you seeing that? There's going to be little dark lines in there.
How little vertical would be vertical power?
parallel to your fingers. Parallel to your fingers.
But it's very, you have to create.
Yeah, you have to be very careful.
Yeah.
You're actually seeing a wave interference pattern. Now, this is actually a single slit wave interference pattern, but it's related to this. The light waves are actually curving. And what you can think of it as having a bunch of little point sources in there, and then those point sources are interfering and giving a wave count. Okay? So even in geometrical optics, the wave theory is still there, still affecting us. And the question is, how much is being affected? And the answer is really weird. And it turns out that you think of the amount of light that hits you, you think, oh, it's proportional to the area. It's actually twice the area of light. It's like you have a cut out of you twice the size. Some of it is, half of it is hitting you, half of it is curving around you. And to prove that, if I remember, this is if your wavelength is much smaller than the wavelength of light. You just say it goes proportional to the geometrical cross-section. But to see where we get the factor of 2 from, if I take a screen, I put a little hole in the screen, you actually get a diffraction pattern there. You get, not only do you get the circle of light, you get waves going around it. Okay? Now, if I take that little hole I cut out and I send light through there, I also get a diffraction pattern around it. This pattern, that pattern have to add up, which means that the light going around it and the light going through, they both have to have the same amount of scattering. So the scattering from this hole is equal to the scattering from that hole, which means if you add it up, we have twice our area of scattering light. It's really kind of freaky. And even though I can see this proof, and I know logically it has to be true, I still can't accept the amount of light my body is affecting is twice the area of my body. But it turns out that's what happens. Okay? So, let's do a calculation on this. We are going to calculate the amount of water in the clouds based on the optical depth of the clouds. Okay? And we're going to be assuming spherical radius of 10 microns. Remember, remote sensing, we always have to make some assumptions here. So that assumption we're going to make. And we've measured an optical depth of 15. You know, however we measure an optical depth, that's what we do. So, what is the total cross-sectional area of all the drops in a vertical column of 1 square meter? You take 1 square meter, cut it out, you cut through the clouds, and take the cross-section of every little drop in there. Now, if I hadn't tried to confuse you in the last 2 slides, there's an answer you should have all said immediately. If the optical depth is 15, I'm looking through a cross-section of 1 square meter. You should see a total cross-section of 15 square meters, because that's what optical depth means, right? Optical depth of 1 means you completely fill up the area. Optical depth of 2 means you fill up the area twice. Optical depth of 15 means you fill up the area 15 times. However, I told you that it actually affects twice the area. So, geometrical. I only need 7.5 square meters to produce the same effects of a cross-section of 15. If there wasn't any wave scattering, if I said that optical depth was 15, you have 1 square meter, that would mean there would be 15 square meters of drop area filling it up. However, each little drop affects twice as much light as its own area. So I end up needing only half that amount of area to have my optical depth of 15.
Right.
Okay?
It's twice of it.
Yes. Each drop affects twice as much. Okay? So, does this hammer home the idea of what optical depth means? Think of it as cross-sectional area. Except that a little screwed up because of the factor of 2. Okay? Now, what is the number of drops in this column? Let's see if you can work that out now. So you know the total cross-sectional area, you know the radius of the drops. See if you can figure out the number of drops. And yes, I gave you the answer, but be able to work it out there. This gives me time to start erasing. Not that easy. You can't do it in your heads. You're going to have to write down some equations and do some calculations. Well, it looks like you're working, you don't look like you're stuck, right? You're okay? I can leave you to go for another few minutes? Or do you need some help? By the way, this calculation has nothing to do with remote sensors. If we're flipping through pages, it's not where you're going to figure out how to do this. It's purely geometric. Here's my hints. A total equals
4 finals. One using the area of the sphere, right?
you have to use that. But which area of the sphere? There is the total outside area of the sphere, there's a cross-sectional area. Cross-sectional. So when we get to the area total, we know each sphere has pi r squared, the cross-sectional area, that's what you see.
Divided by the surface of each drop.
Well, yeah, but this is one drop. What else do I need for the total area? How about the number of drops, right? Based on this, can you now figure out how many drops there are in that column? Okay, work out the number of drops in the column.
2.38 10 power 10.
Yeah. Effective. How about there?
7.5
N is equal to A total over pi r squared. But their total area? 7.5. And now we have to say 10 to the minus 5th meters squared. Oh, those are going to cancel out. 7.5 over 3.14 times 10 to the 10th. And then that's going to work out to about 2.4. Okay. Now that you have the number of drops, you know how to figure out the total volume, right? By the way, what assumption are we making here?
It's perfect spheres.
Perfect spheres and the drops are the same size here. That's not right, but we have to make an assumption somewhere. B total is the scheduler N. Yeah. Right? Yeah.
Micro, isn't it? 10 to the negative 6.
Micron is, but we have 10 microns.
Oh.
The 10 times 10 to the negative 6. Yeah. Don't worry, I made that same mistake yesterday.
That's the camera that's leading towards the whiteboard. Just that one.
Yeah.
It shows one of these, one that the students can see.
There's right there.
Okay. There's, because when they write on the board,
I'm taking pictures and I'm emailing to them tonight.
oh, okay.
Today.
Because they can't see the board.
Yes, I heard that from there.
Takes like 3 cameras to cover everything.
Yeah, just the board. They
Yeah.
can't see the board, so they email us,
Okay.
and then I'm taking pictures. Even though I did the first day,
Yeah.
I just say I have to run to the doctor, but today I'm coming back. So.
Yeah. Well, it might make sense if we decide to do it this way again, if they have a camera like right here.
Yeah,
When they
but-
get the board.
But still, there's some reflection that they cannot see clearly. Maybe we
Oh.
should use another kind of marker.
Ah, okay.
Yes.
Okay. So we can work out the total volume within that 1 meter square. 10 to the minus 4th cubic meters. And then if we collapse that down, you see how thick it would be. How do you figure out how thick that would be? Volume is equal to height times area, right? So height is equal to volume over area. Well, we already have that, 10 to the minus 4th meters cubed divided by 1 meter squared. 10 to the minus 4th meters, which is 1/10 of a millimeter. Okay? So this cloud of optical depth 15 is kind of like a fair weather cumulus, kind of a small fair weather cumulus. If the whole cloud was one and collapsed down to the ground, it just make a little surface scene. It's not as much water as you may think. Now, a storm cloud, something that rains on you, is maybe you know, a couple hundred. Now, a couple hundred cloud, I have to do this a couple hundred times. That would be like, you know, 10 times what we have here. That's still only going to be a few millimeters thick. And it will collapse down. But do we only get a few millimeters of rain whenever there's a storm? No, we get a lot more. So you may be wondering, either this is wrong, or there's something wrong with the picture of all of the rain in a cloud comes from a cloud. Where does the rain come from? I'm going to give you a hint. Before it rains, what does the air feel like? Right? And after a rain, how does it often feel? Right after, kind of dry. What is the cloud doing? Sucking air in, condensing it, and raining back out. Most of the water that falls in the ground wasn't in the clouds. A cloud is just a process, it's a condensation process. So think of clouds as processes, not as things. And most of the rain that falls is not in the cloud at the time we look at it. It's just cycling through. You have new water condensing out and stuff like that. Okay? So, I'm just going to talk about, let's see, how much time do we have here? 4 minutes. One last thing I'm going to talk about is called the asymmetry factor, where what you have is forward, you're taking it as the cosine of the angle, so forward is positive, backwards is negative. If we have pure forward scattering, the asymmetry factor would be +1. That never happens. If pure backward scattering would be -1. That never happens. Normally you get asymmetry factors in the range of about 0.3 to 0.7. So most of it is forward scattering, some of it is backward scattering. So why did it bring this up? Well, remember we had done the milk scattering. I said we can't really use Beer's law for that. We're going to derive what we can use if you have pure scattering, which is the same thing that you would use for calculating the optical depth of the clouds. So here's the idea. We're going to do what's called sort of a two-stream approximation. I'm actually going to be very mathematically sloppy here, but all of my sloppy mistakes are going to cancel out and I'm going to get the right idea here. So this is kind of a conceptual mathematical argument. So we have light that comes in, and then a fraction of it is going to be backscattered. How much is backscattered? The original intensity times the optical depth times the backscatter. Okay? Makes sense? And then how much would be transmitted? This much is reflected, and there's no absorption. How much is transmitted? I0 minus that. Oops. Wrong way. So we're going to have I0 times 1 minus the backscatter being transmitted. Okay? And then it happens again. It goes up here, it's going to get reflected again. We're going to have the same backscatter factor, except now it's squared because it happened the second time. And we have again the amount that's being transmitted. So we can just keep playing this game over and over again. We keep adding it up. So we're going to have this infinite series here. And this thing, you know about 1 over 1 minus x, right? 1 plus x squared plus x cubed is equal to 1 over 1 minus x. And if it's going positive and negative, then it's 1 over 1 plus x. So we're going to do that simplification, and now we have the transmitted light in terms of the optical depth. Okay? This is what you would use instead of Beer's law if you have pure scattering and multiple scattering. Okay? I could talk to you about all of the approximations I'm making, like we should really be using Beer's law and stuff like that. But like I said, they all cancel out. We end up with the correct formula. So if this is the amount being transmitted, how do you figure out the amount being reflected? Yeah, take the original minus the transmitted, and that's the reflected. So now you have the transmitted and the reflected light from a scattered cloud. And you can figure out the optical depth, and from the optical depth, you can figure out the amount of water volume of all of this. So that's how we figure out how much water are in the clouds. And you can even go further than that. It turns out you can get the average radius as well. That's way more complicated. We're not going to take you through that. But you can get optical depth and average radius at the same time if you're using. But could I do that from one wavelength to get two pieces of information? I have to use two wavelengths because you're looking for two pieces of information. So that's the way these things work. Okay? So I'm not going to have you do any calculations with that. I just want you to be aware that yes, there is a pure scattering equivalent of Beer's law. So Beer's law is kind of like absorbing formula. Okay, so that's our example. Okay. So you have a homework problem. Now this one is a little bit tricky. And what you do is you don't panic. You just start writing down things that you know. A lot of people make the mistake of thinking you can see your way all the way to the end of a problem. You can't see your way all the way to the end of a problem. What you can do is you just break it into pieces here and say, well, I can't figure out the final answer, but I can figure this out. Oh, now that I figured out that out, now I can figure this out, and eventually you're going to work your way to the end. Okay? So we have beam of green light. We know the intensity at the top of the atmosphere, and then we have red light. We know that intensity at the top of the atmosphere. Passes through the atmosphere and through a thin cirrus cloud. The ice particle size is about 20 microns. In the red, you know the optical depth. And you know at the bottom, you know, after it goes through the atmosphere, you measure this amount of intensity. So the question is, what will you measure in the green light? We're going to do everything is scattering, no absorption here. And even though I just gave you a formula here, go ahead and use Beer's law for this, okay? Because you're familiar with that. If you want to have fun, you can use the other one for scattering atmosphere. And let you use Beer's law for this. So you have a bunch of information in the red, figure out what's going to happen in the green. Okay? Any questions? Okay. See you tomorrow. We're talking about thermal radiation.